So hello, before I welcome any of our guests, I'd like to invite those who have not already done so to please subscribe to our YouTube channel, Magnimind Academy, where we upload recorded sessions of these talks so you can watch them later. You can also comment any questions on YouTube or just let us know what you think about today's talk in the comment section. All right, now I would like to welcome Kalyan who will be speaking about trends in AI. At Magnimind, we strive to find speakers like this who can deliver all these great talks filled with current information and a new perspective to go along with our data science education programs. These programs range from focusing on the fundamental skills of data science all the way to helping a career change into the industry. And our goal at Magnimind is for impacting as many careers as we can, and this is just one way that we do so. Krishnamani's career has taken him all over the globe, from working in Italy, India, France, and now the US, with a combined 18 years of experience in the tech industry. Consequently, he speaks 4 different languages and can give a much more global perspective to today's subject. For the past 8 years, Kalyan has worked as an engineer in NVIDIA, a very large graphics company based in the Bay Area. Before his career, he has concluded work with GM and Motorola, working in many different positions like research and computer science. And we at Magnimind today are extremely excited to host him, and please give your full attention now to Kalyan Krishnamani.
Thank you, guys. Let me share my screen. Can you guys see my screen?
Yes, we can.
Presentation mode. So he told several different things. I do not know what expectations you will have. And first of all, thank you to the organizers. It's all difficult time, and I hope you're all staying safe. It's great that you guys are continuing this by organizing these virtual conferences. And just for Thomas, I speak actually 5 different languages, 5 languages very fluently. So that's not going to be a part of this talk, but let's see. So although I named this talk Trends in AI, initially I did not know what to talk about. So there are different things that you can talk about, right? You can talk about different frameworks, you can talk about the latest algorithms, you can talk about just BERT, that alone will last several months, I believe. So, or I can talk about GPUs, the architecture, and so on. But I wanted to keep it simple, a very light talk. So not a lot of math, no math at all, not a lot of algorithms, so that you don't have to think really hard. But I wanted to make sure that I answer some of those questions that I've not spoken about in traditional AI or deep learning talks, all right? And if you pay careful attention, this will also give you enough questions to ask in future talks, which will relate to autonomous driving or healthcare or cloud for AI and several different emerging techniques, all right? So that's the goal. It's going to be a very light talk, so you can sit back and enjoy, but you should also pay careful attention so that you get those thoughts in mind and start thinking, all right? So I will take lots of questions at the end of the talk. Let's get started. So what is this talk about? So this is a very rough plan of the talk. So we will look at the history, not too far ago, but say about 20 or 30 years ago, how the effort to build general artificial intelligence, as they used to call it earlier, how it evolved to the present day artificial intelligence. And then we will look at parallel computing and the many flavors of parallel computing that exist today in hardware. So, and even in software, if you take into account distributed computing. And this is one of the most of the major advances has happened just because of parallel computing in present AI. And we will also look at recent trends, hardware and software. And this is by no means an exhaustive list. It is a very umbrella trends, which means at a very high level, what are the software and hardware trends and where we are getting, and what are the challenges. There are always going to be challenges, right? And how some of these challenges are addressing the trends that we saw in the previous bullet. And we will also speculate the future. I'm not going to call it prediction because it may not come true, right? So it is just my speculation, but it will be derived from all the previous things, what trends we are seeing and what challenges, what are the unsolved problems. And given all these things and the current work that is happening, what can we speculate about the future, or at least what can we hope about the future, right? And what this talk is not about, this is very important, because if you come with the hope of learning any of the bullets in this slide, that means you're going to be a little disappointed. But at least I hope that I will give you some things to learn from this, the next 40 minutes. So I'm not going to talk about any specific AI frameworks. There are several talks, there are several documents where you can look at different frameworks like TensorFlow, PyTorch, and so on. I'm not going to do any performance comparisons because they keep changing and it's not the main goal of this talk. And I'm not going to compare AI algorithms. And I'm not going to talk about any particular training or inference techniques, although I might mention them probably, but I'm not going to talk in detail or even mention in detail some of all the training and inference techniques, right? But what can you take away? I've discounted lots of big terms from saying I'm not going to talk about this, I'm not going to talk about that. So what can you take away from the next 40 minutes? So if you're a new graduate student or if you're in academic research, then you can think about some interesting problems to work on. It's interesting because they are challenging enough and they are important enough that they will advance the field of AI. So this is very useful if you're a graduate student or you're involved in academic research lab, or even if you have a passing interest in academic research. And we will also look at some of the challenges that are waiting to be solved. This is very useful if you're in corporate research. And these challenges, some of these unsolved problems, even if you solve partially, it will lead to wider deployment of AI, right? And we will see some examples of these. And you will also see enough knowledge to discount some hype. I'm not saying AI is hype. I'm just saying it has let us increase our expectations, right? So you will be able to set your expectations properly to a measured extent after the next 40 minutes. But just like many expectations in life, it may not come true, but it is good to tune our expectations from artificial intelligence techniques and algorithms before selling ourselves to it completely, right? So there is something for everyone. So let's get started with history. So there used to be something called symbolic AI, right? What used to be called symbolic AI, the goal of those AI systems, this is more than 20 years ago, was to build general artificial intelligence. Okay? Achieving this general intelligence is really tall goal, which means one system that could solve any problem. And there were some limited successes. I shouldn't even call limited because they were quite extraordinary for those days. So there were lots of applications, planning, for example, like path planning for robots. How do you go from A to B in the most efficient way or the most optimal way, right? And under uncertainty, there might be some obstacles on the way, or under some environment constraints, environment that could only be partially observable. So you cannot see the entire environment and model them accurately, but you have only partial information. And with that, you have to make some decisions, some algorithms to go from one point to the other. And another big application is symbolic reasoning. Some of the techniques that are used even today to reason about the correctness of critical software and hardware were developed as during the era of symbolic AI. So they are just like if you have a C program that is going to fly a plane, then you may want to extract that C program statements as mathematical equations and reason about the correctness of the program using mathematical logic. We'll keep coming back to this. So there are many tools. They are called formal tools. Formal verification is the name of the technique. So they use these reasoning techniques, and most of those techniques were developed during this era of symbolic AI. And there are also heuristics and knowledge representation techniques, which are used in almost every field today. And these work best with static, well-defined problems. What do you mean by well-defined? Well-defined means those problems that could be encoded as rules, and those rules that could be reasoned about using logical reasoning or mathematical logic. Suppose we were to build a natural language processing system, right? For English language, then you will encode rules like, oh, it should have subject, verb, and object, and subject should come first, and then verb, and then object, and so on. And then when the AI system generates a new statement in English language, whatever statement it generates, you will be able to reason about it. Rather, the system will be able to reason about it, saying, okay, I arrived at this statement because this statement follows these rules. And in my statement, this is the subject, this is the verb, this is the object, and it follows all these rules. And I applied these rules in this sequence to arrive at this. All right. So the main things to notice in this slide are the goal was general artificial intelligence, the ones within quotes, and they were arrived at using logical reasoning, right? Using some underlying mathematical logic. So what about today? For the last 10 years, we hear about this neural networks. By neural networks in this slide, I mean all machine learning, deep learning, all these things, the present day neural network. So here the goal is to solve a very specific problem effectively and efficiently. In contrast to the previous symbolic AI, which was to build general artificial intelligence, the goal of present day neural network is to solve a specific problem effectively and efficiently. All right, you have this image recognition, and you have this NLP, you have this reinforcement learning. So why do I say it is specific? Because if you have a network that is great for image classification, you can't really expect it to guarantee the same accuracy when you use the network for NLP, for example, right? So it is specific to the problem at hand. So the network that you train and develop for image recognition works best only on images. You cannot really transfer it to NLP. Again, the same way, the other way around, right? If you build a network for NLP, you cannot really use it for anything else. You have to use it for NLP. You can expect it to work fine as long as the data that you show the system is reasonably close to the data that it has seen before. So how does this work, right? It works on specific domains like image or NLP, and it looks at lots of data. You feed it like millions of training examples. The example that we just saw, if you want to write an algorithm to generate English statements, then rather than encoding the rules of English language, what you do is you show it millions of English statements and then say, okay, try to identify some pattern and just give me a statement that will closely match any of these patterns or derivations of one or more patterns, right? So in this case, it is just pattern matching. It is identifying patterns in millions of statements and trying to build something that will be close to any of the other patterns that it already saw, correct? So in this case, it cannot really reason about once it generates a statement, it will be perfectly valid statement, but it won't be able to reason using some rules saying, oh, I generated this particular statement because of this rule. We can only say, oh, I generated this statement with this accuracy, looking at million other statements, correct? So again, in this slide, the main things to note is the goal is to solve a specific problem rather than a generic problem like symbolic AI. And it's done using pattern matching rather than logical reasoning, right? We will come back to this. So what is in store for the future? So we will put off this slide until the next 40 minutes, because until then we will see what are the trends, what are the challenges of today's AI, and what we can learn from the past and how we can infuse some of those into present day AI, right? We will also see some opportunities, we'll also see some trends and many unsolved problems, okay? So let's jump to parallel computing. So I want to make a quick note here that the underlying theme here is parallel computing, although I'm going to be talking a lot about GPUs because that's what I know about. And actually, it has a very beautiful history when you talk about GPUs, okay? And so we will look at a couple of other systems very briefly. I'll just mention. And then we will look at a couple of other systems and the underlying, oh, sorry. So the underlying goal is anyway, parallel computing. So you don't need to get distracted because of GPUs. You can just think of parallel computing, except for these couple of slides where I'm going to be talking about GPUs more often because that's what I know, right? So let's start looking at GPUs, games, and movies. Until a few years ago, consumer-grade GPUs were only bought by enthusiastic gamers, right? And higher-end GPUs, which are more expensive, were bought by movie studios and agencies involved in supercomputing, like national labs and those design industries, like if you are involved in aircraft design or automobile design, they were using lots of parallel computing, and even oil and natural gas exploration, they were using a lot of supercomputing or parallel computing. And but in popular opinion, if you had a GPU 10 years ago, it's very likely that you were a gamer. So what is it about games and movies that made GPUs very useful? We all know it is parallel computing, but what kind, right? So if you think about games or movies, it is all about object positions. You have a bunch of characters in the games or in the movies, and they keep moving around. They move fast, they burn, there are smoke, cars flying around, and so on, right? So suppose we have this 2D monkey, and we have the location of the monkey, XY coordinates, and we are building a 2D game, and you want to move this monkey to a different position on the screen. What you do is you decide how much to move in the X direction and how much to move in the Y direction. And if it's 3D, you will have one more dimension to add and so on, right? Here in this case, I will move TX in the X direction and TY in the Y direction to reach the new location, correct? Which is nothing but matrix transformation. You take the initial coordinates and multiply it with this new transformation matrix, and what you get is the new coordinate. And we all know that matrix operations are extremely parallel, right? So you can do several computations in parallel because some of the row column operations are independent of another row, another column operations. So there is a lot of parallelism in matrix operations. So it's not just the story toy, it's not just movement of objects, but there are several other things which are just matrix transformation, like rotation. If you want to rotate a monkey, if you want to hang down from a tree, or deformation, if you want to smash the monkey, right? Or any object that is deforming because of stress or reflection, and many more are just matrix transformations, and they are extremely parallel. So this made GPUs really, really good for gaming, right? Because GPUs are nothing but lots and lots, thousands of very small compute cores. If you take an Intel CPU, they also have multiple cores, but they are like 10 or 12. But GPUs, an average GPU will have like 2000 or 3000 cores, right? But they are not as capable as a CPU core. But for these matrix of operations, they are very good, right? So they cannot do much, but whatever they can do, there are lots of tools for you to exploit, right? So what about high performance computing, which is like supercomputing, right? Let's look at some high performance HPC applications and see why GPUs became useful there. So how many people recollect this equation? We have all studied this during our undergrad engineering days. At least for me, I came to realize the scale of the importance of this equation only much later in life, and I feel very ashamed about it. And this is the famous Navier-Stokes equation. It describes the flow of incompressible fluids, and it is very widely used in games to simulate smoke or fire and so on. Whenever you see smoke or fire in movies or games, they are underneath, they are using a variant of this equation to simulate that. So you can just go to YouTube and look at Navier-Stokes equation simulations. Then it's very surprising how difficult it is to simulate and what kind of computation goes inside. And it's very widely used in weather modeling, to model ocean currents, to model turbulence. And if you're involved in automobile design, to model the flow of air around a car or flow of wind around an aircraft wings. These are all modeled using this Navier-Stokes equation or some variant of this Navier-Stokes equation. So that's why GPUs, because these any incompressible fluid, you think of it as different layers, and each layer you model it, and it's a very highly parallel computation. And it's no surprise that all the supercomputers that are involved in such operations like fluid dynamics or design and so on, they use lots of GPUs. So the most expensive supercomputers of all, they are also nothing but the massively parallel computation engines. Like they can be used in geology, right? And they are used in weather forecasts, and they are used in aircraft propulsion design to see how well the blades of an engine can cut through the air. And that requires a lot of computational fluid dynamics, basically the Navier-Stokes equation. And more recently, they have also been used to find cure for this COVID-19 that we are going through, right? So we saw games, we saw movies, which are again matrix transformations of objects, and we also saw this high performance computing applications. They all involve parallel computations, right? And since GPUs have thousands of cores, compute cores, they turned out to be great for such applications. But what about AI and specifically TL? And this is from a blog post I came across recently, and I just decided to use it right away because this is the best description of ML I could find that fits in one slide, right? You have all these features, X1, X2, and you have the weights, you have the weight matrix that you're trying to train and learn, and you see that this tiny network in just one pass involves two sets of matrix multiplications, right? For the first layer and for the second layer, right? So you can contrast this. So you can see the amount of parallelism in this toy example. The ResNet 50, right, one of the benchmarks for image classification, it has 50 layers and about 23 million trainable parameters, I guess. It's of the order of 23 million, right? So you can imagine the scale of parallelism available in such networks, right? So that's why if you have GPUs, the more cores you add to it, you get, magnitude of efficiency more than using CPUs or any other system that is not able to exploit this parallelism. So you know already by looking at this picture, or if I throw in several cores, these matrix operations will get parallelized, and the more cores I have, the better I can compute, correct? But why only now? It's not that GPUs were invented only in the last 5 or 10 years. GPUs are not something new. We had GPUs for decades. Maybe those GPUs 20 years ago were not as powerful as the ones that we have today, but we still had them, right? And they've been around for around 20 years at least. And the idea of using GPUs for machine learning, that's also not new. If you read this research paper using GPUs for machine learning, this is from 2005, right? 15 years ago. And it already shows some moderate speed up, but not many people, Facebook, Google, they were not using this 15 years ago, right? And we all know HPC, gaming, visual effects, all these have been around for decades. We all have seen Jurassic Park and all those things. So how did AI and GPU get into the limelight only now? So there are three big factors that led to this GPUs coming to the limelight. I shouldn't even say GPUs. In general, parallel computing and for machine learning, bringing that to the limelight, there are three big factors. The first of all is big data, because almost everyone has a smartphone, right? And the sensors have become really, really inexpensive. Your camera is a sensor. It is an image sensor, right? And all smartphones have at least one image sensor, at least one camera. And usually we make it a point to photograph our food, even if we don't end up eating it eventually, right? And there was this proliferation of internet, mobile internet in particular, that made sure that we can share the images that we take with everyone, and everyone can share it and send it around and so on. And it's not just images. As you can see in this snapshot, we are generating lots and lots of data every minute of the day. It's not just images, but there are several kinds of data. So someone is gathering all this data, and they need more and more parallel computers to digest this data, to make sense of this data, right? So having data, just having lots and lots of data is not enough. So this is, although the biggest factor, it generated lots of data. So now you need to build bigger computers to sit and analyze this big data, right? And again, The second factor is computing power, and mostly helped by Moore's law and other technology innovations, right? So this news article, right, even the headline sends the message. Actually, your smartphone is millions of times more powerful than Apollo 11's guidance computers, right? So we may decide to use our pocket computers only to poke our friends in Facebook, but it is still a very, very capable computer. And another factor is distributed computing. You can think of Gmail, you can think of other Google services like Google Maps, or you can think of AWS and so on, right? So if you cannot do it in one desktop computer, you just distribute the computation and gather and accumulate the results. And we were able to get away by distributing the computation, we were able to handle lots of data. The other one is growth of data centers. I'm saying this is one of the big factors because today you don't need to own and maintain an expensive compute infrastructure anymore. We can just rent it out as needed and give it back when our computation is done, right? So the first big factor is big data. The second big factor is computing power. And the third factor is software platform. It's not enough if you have lots of data and really massive computing engine, but you should be able to exploit that computing architecture, right? You should be able to program that architecture so that you can get what you want out of it. So something like CUDA that allowed us to program and distribute our computations into the many thousands of GPU cores. And we have libraries today that accelerate even the DNN operations like softmax, ReLU, and all those things. They're called QDNN, like CUDA deep neural network libraries, right? So these three factors, primarily the first two, big data and computing power, they are relatively new. We did not have awesome phones 15 years ago, although we had this computing power. We had GPUs around 20 years ago, as we saw, but we didn't have lots of data because we didn't have lots of smartphones and cameras. They were still expensive, so we were not generating lots of data, right? And even computing power, it wasn't really affordable, correct? So you had to buy even relatively efficient or powerful desktop was pretty expensive those days. But they were used for high performance computing because supercomputers, the national labs could afford it, and they had to afford it in order to model weather and so on, correct? So have these three big factors in mind. Now, let us turn to some of the challenges. So not everything is good news. Although we have all these wonderful systems, there are still challenges because we are getting more and more data, more and more computation, but there is still bad news, right? There are lots of challenges. So let's see some of the challenges and what are the trends, what people are doing to overcome some of these challenges. Let us start with hardware challenges, right? So as we saw, we have more and more data, and to train our networks, we saw that in ResNet 50, there are like 23 million trainable parameters. So we need to read more and more data from the memory, right? So GPU is nothing but lots and lots, thousands of compute cores. And if you want to do any useful computation with data using those cores, what you need to do is to move the data from the memory all the way into the compute cores, perform the computation, and then write back the result into the memory. So, which is expensive, right? You have more and more data, so you're doing lots of reads and writes to the memory. So that itself is a big challenge because the data pipe, that is the pipe between the memory and your compute cores, you can think of, at some point when we stuff more and more compute cores, the reading and writing to memory is going to be a big bottleneck because you can only read and write at certain speed, and that is dictated by physics, right? Movement of electrons and so on. So at some point, you will anyway have a bottleneck. And these parameters and models also keep growing, and reading and to and fro memory is very expensive with respect to both time and power. This is a slide from Bill Daly's talk. It's already, you see it's 5 years old. It shows how much energy is spent in computation, the green box, compared to the energy spent in reading the operands to do the computation. So you see that you spend 20 picojoules to do some 64-bit computation. But in order to do the computation, you spend 16 nanojoules to read operands from the memory, right? 16 nanojoules is 16,000 picojoules. So you are spending 16,000 picojoules to do some operation that is only 20 picojoules, all right? So it's a lot of effort. So more read and write you do to memory, the more power you're going to burn, correct? And at some point, it's going to hit your efficiency. And there are also evolving, and you can build bigger chips, as we'll see, there are some people who are building it, but again, you have to be very conscious of the power that you spend. And there are also some evolving techniques that the underlying hardware architecture needs to be aware of. So hardware is not like software, right? When you're building hardware, you cannot sell a patch. You cannot say, oh, this is the patch, you download it, and your hardware will have a new functionality, correct? It's mostly many things are baked in, although you can control certain things using some registers, but most of the code functionality is baked in to the silicon, right? So you need to think about many of these evolving techniques like quantization, mixed precision training, and so on, when you build the architecture so that the SDK or your compute platform can make use of the hardware architecture when they use all these features, right? So these are all the challenges. You may think that, oh, all the challenges, it's only one slide worth. No, these are lots, right? If you think about it, each and every of these challenge may require several thousand engineers or several years or several techniques to overcome. So what are the people doing about it? What are the trends in hardware, right? So there are some people who are really bold enough to build bigger processors. And this is the Cerebras processor. As you see, you would have heard about the Cerebras computer and that company. It is 56 times the size of a GPU. Just to put it in perspective, right? The pan that I use to make omelette is 8 inches in diameter. And this guy is bigger than that. As you see, it's 8.5 inches, correct? So just imagine the size. Just imagine, and you could even stack up several of these things and achieve more parallelism, correct? And there are also model compression techniques. This is more in the case of inference side, because the model keeps growing bigger and bigger, and you may want to fit it in a small chip, an inference chip. So people try to do some compression, like if there are lots of sparse matrices, lots of zeros, then the hardware should be able to detect it and kind of squash it, because you don't achieve anything by having 0 rows or 0 columns when you multiply matrices. So these are the things, again, you need to keep in mind when you build hardware. So there are lots of these techniques that are getting into computer architecture, like hardware design, right? And there's also this in-memory computing. This has been in research for a very long time, but there is considerable interest in this very lately, right? The idea being that instead of moving data, we saw in the previous slide that moving data is very, very expensive. Instead of moving data, which is very energy, the cost of energy for moving data is very high, why don't we just move compute to the place where data resides? So, which is the memory, right? Why don't you put some cheap compute elements wherever there is the data, which is the memory, and just compute it and write back to the memory there itself, right? So there are some chips that do in-memory computing, but we'll have to wait and see whether it becomes mainstream. And again, model parallelism and data parallelism, we keep generating more and more data. So now what do? You divide the network into several pieces and distribute them to a cluster of GPUs and train them, and then correlate the results, just like how AWS or the distributed computing does, right? Or you can even divide the data and distribute it to different machines, right? You have this model parallelism and data parallelism. These are not very new, but they are still trying to get the best model parallelism, best data parallelism, the best batch size, and so on, correct? And now you also talk about binary quantization and hardware and compiler optimizations. So these are also some of the things that you need to keep in mind while designing your hardware. So I would say that if you are interested in computer architecture, this is the best time to be a computer architect because it's very challenging and you will learn a lot just by being a computer architect. You will know about programming languages, you will know about hardware, you will know about optimization techniques, core mathematics, but you may want to use some of those techniques to make sure the register utilization and allocation is optimal, right? So now we saw some hardware trends and challenges. It's not that software is without any challenge, right? And it is expected, it is very obvious. So because if I ask you what's your favorite programming language, very likely your answer is going to be something like, I learned C, I'm good at Java, I'm learning to like Python because of deep learning, but my company uses Julia. It is something to that effect, right? Most of us. And that is okay, that's how it is, right? And that's how it has always been. And similarly, only when you talk about deep learning, there are different frameworks, TensorFlow, Keras, PyTorch, and all those things. And some of them claim to be great for research, and some others claim to be great for production and deployment. But which one is better? You will never get a clear answer because there isn't one. It depends on lots of other factors, right? And there are also different optimizing compilers for inference, right? Again, which one is the best optimizing compiler? It depends on the network. It depends on several other factors. And there are also different applications that require different algorithms. BERT itself is new, right? It's for language processing. And I think it came in 2019 or end of 2018. But now you have several variants for each domain, BioBERT for biology and VideoBERT for video and so on, right? So again, which one is the best? It depends on several factors, mainly your domain, correct? And there are also evolving algorithms. There are neuroevolutionary algorithms which try to borrow techniques from other domains and apply it for this deep learning and so on. So these are not only software challenges, but now if you ask me, why don't we just build a chip that is very good for image processing and just sell it to Facebook and all other people who are doing image processing, right? Or image classification. That itself, the software challenge is the reason because the algorithms keep evolving. The algorithm is not stable. So by the time you design a chip and build it, the algorithm would have evolved and there might be a better algorithm and your hardware would be of no use. So once the algorithm stabilize, only then you can think about building a application specific chip to handle that, right? So there are these evolving algorithms and there are also different infrastructures. You wouldn't be happy if your accuracy is going to drop when you move from one infrastructure to the other, right? If you move from cloud GPUs to cloud TPUs, you would expect accuracy to go up or at least stay the same and not drop, right? This is another challenge because most of the workloads are moving to the cloud and you don't want to lose anything just by doing that. So what are the trends in software? How are some of these challenges being addressed? So the first big trend is things like auto ML and driverless AI and so on. These are the things that are making ML more easy and adoptable by many. So it used to be the case that, oh, you learn Python, you learn Keras, or you learn TensorFlow, or PyTorch, and then you start playing around with large data sets and then you learn deep learning. But today, for most applications, you can just do AutoML, you can use it. It is just very graphical user interface. It has a very beautiful one. It is very intuitive and to some extent, you may not be able to optimize it or fine tune it, but to some extent, if you have lots of data, you can just try to analyze the data and train and build some models, right? That will be the first step. And that is very possible. It has made this kind of machine learning accessible to many. You don't need to learn a new programming language and become a champ at it before you start training models, correct? And as we get more and more data, and more larger and larger networks, you want to distribute them. And there are libraries like Horoword from Uber and TensorFlow Collective. They help in distributing these kind of training. And with IoT, or what we call edge AI devices, you need to build small enough models because most of these edge AI devices, the inference chips, are very uh, sensitive to power consumption, right? You don't want to, they have a small battery and you cannot afford to burn away a lot of power. So you want to optimize your model so that they burn very little power. At the same time, they should not drop their inference accuracy. They should do it really well. And we also see algorithmic ideas from other fields like neuroevolutionary computing. What it does is borrows techniques from genetic algorithms to find better hyperparameters for your deep learning neural networks, right? And similarly, there is some effort to infuse some techniques from symbolic reasoning to reason about some of the decisions made by the current day neural networks, which basically depend on pattern matching and security. And this should be the first bullet on my very first slide because it's very, very important. And many of the security and encryption techniques are receiving renewed interest just because of cloud computing and primarily because of deep learning, because most of the deep learning workloads are moving to the cloud or performed in the cloud. And this is mostly with respect to apps that have critical data like personal data or medical data and so on. So all these techniques you would have heard about differential privacy, fully homomorphic encryption, none of these techniques is new. They have been existing for several decades, but the deep learning and the cloud computing have pushed it or made it very, very attractive today. So let us start, given all these challenges and what are the trends that are happening, let us speculate some of the what we can expect from future AI. So there are many unsolved problems. So I'm going to speculate that at least some of these things should be solved. I'm not even saying I hope they are solved because I'm saying they should be solved in order for AI to be more widely adopted, right? The first is explainable AI. This is one of my personal favorites. There is no reliable way today to explain the choices or decisions made by a DL algorithm. There is some research that has provided some results, but if you take any large scale AI system, it's very likely it cannot explain even an image classification system that classifies images of dogs and cats. It really cannot explain why it classified a dog image as a dog, right? It cannot really do any reasoning behind it. It can only say, oh, the accuracy is 95%, and we just compute this accuracy and just rely on that. And there's also the symbolic AI and deep learning. This is kind of promising because it is trying to explain some of the decisions, but because you used pattern matching to learn, symbolic AI can not do much, or at least as of now, they haven't exploited the techniques of symbolic AI well enough that it is able to explain all the decisions, all the intermediate neural network layers, whatever it decided, they are not able to do that. But hopefully, this infusion of these techniques will be promising. And this might be one of those techniques that will lead to explainable AI. We have to wait and see. The other thing is because of distributed training, the GPU utilization in clusters for deep learning workloads has become a big challenge. There's a very recent Microsoft research paper that talks about GPU utilization. They have profiled the utilization of several GPUs in a cluster for different workloads. And you can imagine that's bound to happen, right? Because the workloads themselves are very dynamic. So you cannot really fine tune a distributed network of GPUs so that each and every GPU is utilized to the best possible extent when you do not know the shape and size and the behavior of the workloads, which are the inputs to the system, correct? So it is a very challenging problem, but you may want to solve it because if you are renting a GPU cluster, you want to make the best use of it, right? You don't want only a few GPUs working 100% and most of them spending only 50% of their effort because you're paying for them. You want to use them to the best extent, correct? And security, again, as I told, this should have been the first bullet point. I don't know how to convince that security is one of the most important aspects. So I'm just going to show some recent news clips, and I will let you convince yourself that you're using at least one of those applications that got hacked or that got exploited, right? It's not that the it's not about the specific application, but you may think about any equivalent application, right? For example, it's not about Uber. You can think about any ride hailing service or any the sharing service, correct? And you can think about Instagram, which is a social network, again, Facebook, again, Docker Hub, correct? So this should have already convinced you that you would have used at least one of them. You would have a bank account, you would have a social network account, or you would have used Uber. So the security, if you look at all these things, all these companies have enough manpower to work on security, to do research on security, but they are doing great work. But the security is such a big challenge because it's very difficult. The hackers are always smarter than the engineers who build them, right? Because you cannot think of all possible scenarios. Things can go wrong. So given all these things, what can we expect from AI of tomorrow? It looks like I spoke about a lot of bad news, right? But there are like, we saw lots of advancements in security and so on. So what can we expect from the AI of tomorrow? What does it look like based on what we saw with respect to the trends and challenges and so on? So the goal, it is just my opinion and it's just my belief. The goal, I believe, would be to be able to explain the outcome, to explain why it categorized or made some decision. A deep learning neural network made some decision, right? And that is reasonable to expect. And in order to do that, it has to understand the context in which the system is operating. Suppose I were to make an English statement today, right? It is almost impossible for any AI algorithm today to tell me if I made a serious statement or my statement was sarcastic, right? It is almost impossible. Again, if I were to post a violent video involving me, it is very challenging to decide if I'm really committing some violence or is it some movie trailer, some violent movie in which I'm an actor, correct? So these are the kind of problems the social media companies like Twitter and Facebook are dealing with today. It's a really challenging problem. It's very difficult to automate. You need to know the context, correct? You need to know whether the video is of a movie trailer or some homemade movie or it's some really violent thing happening, right? Before you decide to pull it down. So understanding the context, it's very difficult. Today's deep learning systems do not have a way to encode the context to inform the system that, oh, this is the context. There is some limited success, like you would have seen. You take all the tweets and identify whether it's a good tweet or what is the mood and so on, but they are only very limited. It cannot go beyond that as of today, correct? And the other one is you want to be able to reason about the decisions. For example, if you have a cancer diagnostic deep learning algorithm, right? If it is going to categorize something, some tissue as a cancerous tissue, you better know, it better explain you why it made that choice, because these decisions, if they go wrong, can have profound implications, correct? So the way they handle it today is by having a human counterpart and trying to aid the human counterpart with this deep learning algorithm so that if this algorithm happens to make a mistake, he can correct it and so on. But in future, it may not be the case, at least from what we are made to believe, right? So before we end up in a day where the deep learning algorithms are going to make the choice, we may want to have this deep learning system also know how to tell us what led the algorithm to make the choice that it made, to give me a set of sequences, right? Set of steps. Oh, I made this is what made me make this choice, right? Rather than just numbers like, oh, I'm 95% accurate, but you can be 5% wrong, right? And those implications are going to be very serious. And it should be able to make high stake decisions. By high stake, you can think of autonomous car merging onto a highway, or surgical robot, or again, the example we saw, medical diagnostics, right? Those are really high stake decisions because the implications are very serious, and they should be able to do it in a secure environment, right? Because you don't want a hacker to hack into the system and then modify the decisions, correct? You don't want any intruder to influence the decisions of the algorithm. First of all, the algorithm has to be correct. It should be able to explain itself. And number two, it should not be possible for an intruder to modify a correct algorithm and influence it, correct? And these all encapsulate what I meant by explainable AI, right? So what about this general artificial intelligence that we saw, the symbolic AI? More than 20 years ago, there was a lot of effort, right? But it kind of fizzled out. And then we ended up in this deep learning, which is working really well. But again, it's not able to explain, and we are kind of stuck. Oh, we are using deep learning. It explains we have 95% accuracy, but we are not able to make the kind of explanations that the general AI, which didn't scale that well, but at least was able to give some logical reasoning. What do we do? So I do not know how many of you have read this book called Thinking Fast and Slow by Daniel Kahneman. It's a wonderful book. So this is basically about behavioral psychology. So Daniel Kahneman says that our brain or our behavior has system one and system two modes, right? So we invoke system one for our routine activities, like the ones we are accustomed to, like driving in a busy highway. We don't really think too hard, right? We are just automated. We just drive, we just navigate the road, or switching between different languages while speaking. Like when I switch between English and some Indian language, English sentence structures are like subject, verb, and object. And most of the Indian languages that I know, the sentence structure is subject, object, and verb. And my brain, without putting any effort, it is able to switch between these structures, which is phenomenal actually when you think about it. Not many computer algorithms can do that. So these are all system one because I have seen these sentence patterns, right, when I was growing up, and I have learned through pattern matching, correct? So the system one has over the years learned from patterns, and it is really fast and it is really habitual. You need not think deep in order to do it. But when you're asked to solve a math problem, right, some differentiation of something, unless you're a math genius, you will have to sit down and think, right? You have to retrieve some deep knowledge from your memory and some logical reasoning, and you have to solve that problem. So you cannot do it as in an automated fashion as you drive in a busy highway, correct? You need to put some effort. That is pretty slow, but it involves more thinking and it involves more logical reasoning. Whereas while driving in a highway, you'll just cut across someone else. And if I ask you, oh, why did you do that? You would say, oh, I was frustrated. I just felt like doing it. You don't have any logical reason, right? Whereas if you have to solve a math problem, you will have that logical reason because that is called system two, right? And if any of you have watched Joshua Bengio's Neurips talk last year, he made a very beautiful analogy between system one and system two deep learning systems, right? With respect to AI. He calls the present day AI system system one because it has learned using pattern matching. It is really fast. It may not do logical reasoning, but it is really fast because we give lots of data and it's kind of a very habitual system. And he says that we have to move towards system 2 AI, which will be able to give explanations, which may be slow, but that's all right. Let it be slow, but it will be able to explain the decisions that it made. It will be able to understand the context. It will be able to do logical decision making. Right? It's a very brilliant talk, and I highly recommend this talk. It's there on YouTube. You can just go and watch it. But there is some effort merging symbolic AI and the present day deep learning systems, but they are more academic as of now. We don't see it in really large scale systems, but the hope is that it's going to be the future. At least it has to be if we have to adopt these deep learning systems and very critical softwares like self-driving cars or medical diagnostics and so on, right? So this is my speculation and my hope for the future of AI. So let's recap. What did we learn in the last 40 minutes? Right. So why GPUs for AI? It's parallelism or massive parallelism. It's not only GPUs. You know about Google's TPUs, and TPU is not a new invention. The concept called systolic arrays has been there for at least 30 years, I believe. There's a paper from the 1980s or 90s, which talks about systolic arrays, and TPUs are nothing but systolic arrays. Again, there are parallel computers, right? And again, you would have heard about this company called GraphCore, which makes something called IPU, which is again parallel processing elements, right? They are all new architectures, new hardwares, but the concepts has been there for a very, very long time. So what is the initial goal of AI and what are the goals today? We saw that we started with symbolic AI more than a couple of decades ago. We gave up because we didn't have powerful computers, we didn't have a lot of data, and it was very difficult to solve a general problem, right? It was very difficult to encode. If you were to do NLP, you have to encode the rules of the sentence structures, of the grammar, and so on for each and every language. And that was not scalable at that time with those computing techniques that were available those days. And then we saw this deep learning techniques. We have lots and lots of data, and it works really awesome, but we find ourselves unable to explain our algorithms decisions. And now we are trying to go back and use some of the lessons from symbolic AI and try to merge or use some of those lessons to reason about the decisions that we make using our present day deep learning systems. And what can we expect from AI, and why should we expect whatever we expect? We have to expect AI to explain the decisions. As we saw, there are lots of critical things, right? We may want to do it because there's no choice otherwise if we were to deploy it in very critical applications. And the other one is security. We want them to be secure because we are doing more and more in the cloud, and we don't want anyone to alter the decisions, correct? So that is another expectation. And what are the other areas that are developing because of AI? The number one is computer architecture. We only had the Intel CPU architecture and GPU architecture, but today you have a wide array of architectures, right? TPUs and the GraphCore, IPUs, and Cerebras, and Grok, which is a very new thing, which relies more on compiler and some parallel hardware architecture and so on. So this is the best time to be a computer architect. And not only computer architecture, security, as we already saw, techniques like fully homomorphic encryption, differential privacy, federated learning, these are all having a red carpet treatment today, right? So that's all I have. But before I end, I came across this image in a blog post, and although it's a very silly thing, let me explain this. This is about some image classification, that is classifying images of puppies and muffins. So you can just imagine this algorithm getting installed in your self-driving car. So it's very likely that you wouldn't want your car to be stuck in the middle of a highway because it saw a puppy, when in reality, it was a muffin tossed out from the car in front of yours, right? And on the other hand, most likely, you wouldn't like your car to run over a puppy, mistaking it for a muffin, right? So although this is a very silly example and very small, funny example, I believe it should help you tune your expectations, right? What do you want from such a system that is going to classify puppies and muffins if it were to be installed in my car, right? What can I expect and what should I hope for, correct? And at least that's what you need to think about. And in your future talks, when someone talks about autonomous driving or medical AI, you should be able to ask the right questions. So that's all I have. Any questions? I can take questions now.
Awesome. Thank you so much, Kalyan. We have one question in the Q&A tab currently.
Yeah, let me see.
Do you see that right next to the share screen button?
Next to the share screen. What is your guess for when computers will have human level general intelligence, right? That's the question. So, well, I cannot put a real time frame. I can only speculate. Rather than putting a time frame, I can say that it will have partial human level general intelligence only when we are able to do that system to deep learning. That is, only when we are able to explain the decisions. Today's deep learning cannot explain anything, correct? If you, even for cat and dog image classification, it cannot really explain why it categorizes something as a cat or a dog, correct? Only when we go towards that, we can at least aspire to be human level general intelligence. And this human level is a very tall goal, right? Because I've seen many talks that say, oh, the human brain works this way, and that's why this is going to work much better. But in reality, if you talk to doctors or scientists, they will tell you that we don't even know how an earthworm's brain works completely, right? So human brain is far away. Even the earthworm's brain, we do not know. We know some aspects of it. We know that, oh, it has these sensors and so on, but we really do not know the complete picture. So it's very difficult to build a system that will mimic. Other than cloud, where else can processing be done? Is there an edge processing needed? Example, autonomous cars. Okay, edge and cloud. I mean, you can have edge processing in the cloud. Now you may want to divide this into two, training and inference. So first thing is training, which is very expensive. You need lots of GPUs. Basically, you're trying to fit an equation after feeding in lots of data, like millions of data points, and trying to ask the system, okay, now give me an equation if I have several features, right? For example, which day of the week you poked your friend on Facebook. Was it a weekday? Was it a weekend? And what time was it? And so on. These are all the different features, correct? So Facebook, in its deep learning algorithm, might be using millions of features to predict when you're most likely to poke someone else, or what is the what kind of news feed to show you, correct? So that is training. Training is very expensive, and then you get an equation, right? That is your model. So when you see new data, you feed it to that equation, just substitute values and get an answer. That is your inference, correct? So this edge is several edge sensors. For example, for traffic light, you train a huge network, feeding it billions of images of traffic intersections or highways and so on. You will get an equation, and you put it in a small chip, an inference chip, or an edge computer on a traffic pole, the light pole. And when you see a new image, it has to be able to infer using the training data, using the trained model. So you train the model separately, and then you put it in the inference chip. And that's why inference chips are typically small and they are very power efficient. That's why you may want to compress the model. So the edge processing is needed there, right? You may want to process it really fast at the edge. That's why the model has to be small. It has to be very well optimized. Example, autonomous cars. That is a very good point. So most of the autonomous cars and all those things, they are really betting on faster internet connectivity, right? So they want to be able to communicate with the network because you can only have so much memory and power in the car. Because when you think about an autonomous car, it is not just one processor, right? It has a bunch of sensors which is collecting very heavy data like video frames. They're very heavy, right? You need lots of memory. So once 5G promise becomes fruitful, then at least you will be able to communicate those trained data, the model, and infer it very quickly. But till then, as of today, most of the computation is being done in the trunk of the car, right? And they are really huge computers, and it may not scale to millions of cars because they are, first of all, really huge, and they may consume lots of resources like power and space and so on. What other examples like that cannot be done in the cloud? First of all, I don't believe it cannot be done in the cloud. It can be done in the cloud, but there are lots of drawbacks, right? First of all, latency. If you're, doing some robotic surgery, correct? And if you want to rely on the internet connectivity,
to be able for the surgery to be precise, you don't want to do it at the cloud, at least as of today, because you cannot really trust the latency, correct? It may go down, all of a sudden AWS might go down and so on. And you don't really want that in the case of robotic surgery. Whereas if you're trying to predict a news feed in Facebook, even if you are a few minutes delayed, that's okay. It's not that critical, correct? You may lose a few advertising cents, but that's not that critical, correct? So there are examples that cannot be done in the cloud today. It is feasible, but it's not being done in the cloud because of these latency issues, and most of the financial things are not done in the cloud because of security issues and so on. So how do you see the role of federated learning play with respect to usage of GPUs? Well, I do not have the actual numbers, but there are many people who are using federated learning and they are using GPUs. But in general, the usage of GPUs, if you want to optimize the usage, then you should know the workload really well. Otherwise, it will be underutilized, but that's fine. Even for federated learning, almost many of those big telecom companies are using GPUs for federated learning. How do you think about quantum computers? Oh, I'm not really qualified to answer this, but I believe there's a lot of promise in quantum computing, but I do not know how it will improve AI or ML. The only thing is it will make these algorithms much faster, but I do not know about the size. If you see the present day quantum computers, they are not like you can carry it in your pocket, correct? So they are really huge and they need really precise environment, right? There are many conditions. It's like specific temperature, specific conditions, right? It's not like your laptop or mobile phone that you can just carry it in your pocket in the rain, in the sun, and so on. So only when those things are solved, we will see quantum computers becoming mainstream. But at least if you see the last 10 years, there has been a tremendous progress in quantum computers. At least with that size, they are able to solve bigger and bigger problems. And having said that, if quantum computers become mainstream, it's a big challenge for security. Most of the security encryption techniques that we have today is going to break. So that's a big challenge. Overnight, you may have to change the encryption, decryption, all those techniques in all the banks all around the world. That's going to be really impossible. So they are just hoping that quantum computers are not going to be super successful and mainstream overnight, right? So before that, you have to develop all these security practices. So a few years ago, I used to say that if you want a job for the next 1 or 2 years, you go and learn web development, right? Like JavaScript and so on. And if you want a job for the next 10 years, you go and learn deep learning. And if you want to have a job for the rest of your life, that means you go and work in computer security. And that statement holds even today, right? Why isn't CUDA available for a Mac Pro? Oh, I wouldn't know, man. I have to ask NVIDIA. I believe it was available until 2015 or something, and I don't even use a Mac, so I wouldn't know. All right, sorry about that. I do not know when it will be available or something. You may have to ask in some NVIDIA channel, right? Can I get a copy of the presentation? Yes, I have sent the copy, a PDF file, and I think April will be able to upload it along with this talk. Any more questions?
I've shared a question from chat. Can you check it?
Okay. When I open the chat, shows question and answer. Wait a second. Let me stop sharing and then go back to the chat. Okay, now I can see. Cool, I see lots of questions. Do we have any AI agent that is capable of solving multitask instead of a specific task?
I don't really understand what is oh, you're asking whether there is one AI algorithm that can solve image and NLP and so on. There are people who are trying to use the RNN networks for other tasks and so on, but even if it is able to solve, it won't be able to solve to the same accuracy. So you have to tweak it. You have to do lots of changes to it before it becomes useful. So if you are saying it is capable of solving, yes, it will solve, but it will give a very bad solution. So you may have to spend lots of effort. So there is no general solution for any specific AI task. Will we be able to review the slides later? Yes. Are FPGAs being used instead of GPUs? Yes, there are FPGAs being used, but it comes to programmability, right? Because there are different levels of programmability. FPGAs are more widely used where you download some program onto the FPGA and forget it, and it remains there for a very long time, right? So suppose you want to put something on the field to send something under the ocean or whatever. So you download that program into the FPGA and forget it. You don't reprogram it for a very long time. But that application is very different from what things like GPUs are used for, right? It is reprogrammable multiple times and you can program it very easily using, that's why this CUDA and all those things drive that development. And if you talk about other GPUs, there is this OpenCL. So there's always this, which is better, OpenCL or CUDA. But if you see, most of these frameworks, TensorFlow, PyTorch, all those things, the backend, they use this QDNN and CUDA backends, correct? So they are all optimized for the present day GPUs. Although FPGAs are being used, but with respect to programmability, more people are preferring GPUs over FPGAs. But there might be some applications where you don't need a lot of this programming flexibility, but you just want to download it once and then forget about it. In those cases, people still use FPGAs. Are there any more questions? Let me look through this.
Looks like there's two more in the Q&A section that just popped up.
Okay. New ideas and products in home. Oh, okay. In home automation, what new profit ideas do you see? Well, I do not know, but this Alexa, the voice NLP is a big thing. That's why BERT has taken off like anything. If you just type BERT and variants into Google, you will see how many variants are there. And natural language processing, right? Alexa just started as a small toy, and now almost every home and every mobile phone has some version of it, whether you call it OK Google or Siri or something, correct? And most of these are going to be voice driven. I even know of fighter jets which have some voice control, right? I do not know how many of you know about this Rafale from Dassault Aviation. Is a fighter jet, and it has some amount of voice activated commands, right? So voice activation is going to be very important. And with respect to home automation, you already see Nest is very popular. Things like Nest are very popular. But with respect to profit, I wouldn't know, right? It depends on whether there will be only one or two big players who will run the show, or if you are a small player, how much you can get, I wouldn't know. New ideas and products in home automation. Well, again, more and more, right? One thing that doesn't exist today, and it's also difficult to do, is you set a budget. Okay, I do not want to pay more than so many dollars for my utility bills, right? Electricity and so on. And you may want to develop a home automation system that tries to turn off the light and other utilities so that to maintain that budget, right? But most of the home automation systems today are not geared towards those customers, right? So I have tried to build such systems like very recently, like 2 years ago, using this
what is that, the Pi computer. But it turned out that if you set those budgets, it will keep turning on and off the light so often that switching itself will end up burning more power. So it's not a very straightforward solution. It's a very interesting optimization problem. So how often to switch on and off the light while at the same time not end up burning lots of power just because of this switching on and off, correct? So that's another interesting thing, but there are lots of players and lots of new things that are coming up. So there might be many more ideas. This is just one idea that I worked with and I completely failed because it was spending more energy than required just by switching on and off. To what extent is causality being considered in ML pipelines? It is really being considered when it mostly in time series applications. If you see, if you look at the stock prediction and all those things, even if you go to Google Finance and look at some stock ticker, they will tag several important events, right? So if whatever came in the news, if it is about some big thing that happened with the company, say Google announced something big, then they will tag that news item along with that specific series data. So when you plot that time series, then you will know, oh, if there is a dip, then you look at those tags and see, try to see if this is the cause of that dip. It may not be, but probably when you start tagging more and more, you might be able to find some similarities. But it may also be the case that there will be lots of noise that you may have to filter out before identifying the real cause. But it is more common in time series data. If you see, you can just go to Google Finance and look for any volatile stock ticker, right? And it will show you, if you, I think it's Google or Yahoo Finance, I think Google Finance, that chart, it will show you, it will tag lots of events on the Google News feeds for many of those dates. Is there a higher level programming language for scientific computing on GPUs? There are many actually, although most of them boil down to CUDA. If you look at, there are lots of research languages, but I do not know, most of these national labs, they don't use these higher level programming languages for scientific computing on GPUs because any such abstraction might lead to kind of less optimal code, right? Even on an Intel CPU, if you have to write your own machine code, that's going to be the most optimal because you are going to be using the registers and all those things very efficiently. You are working at such a low level, but that became very tedious for really large programs. And that's why these higher level programming languages like C and all those guys became very popular. And the compiler optimizations got better and better. So you could squeeze out lots of performance just by doing this machine translation from high level language like C onto machine code. Whereas for several high performance computing applications like scientific computing, you cannot afford to have some inaccuracies. That's why they work in really high precision. You cannot really live with quantized data, right? Because it will be like, oh, I don't need 32-bit data. I will just quantize it. I will just use 8 bits. I will just round up a certain thing. Those things will affect a lot of weather forecasting and, you know, thermodynamics and so on. So scientific computing, they tend to rely on these high precision computing, right? So there are high level programming languages. I don't get anything out of the mind, but there are many research level languages which I don't want to suggest because those things will keep changing. And mostly people in high performance computing labs, they tend to write it using CUDA, and they use several other libraries to make it even more efficient. Can I get a certificate for this webinar? I do not know the answers. Are there any more questions?
It looks like that's it. Typically, we don't really give out certificates for these webinars. They're more for just the general help of anyone who wants to come. But thank you all for attending the talk, and thank you, Kalyan, for your time.
No problem.
We hold these talks with the hopes to more inspire people to just keep furthering your learning, and anyone who came here has done that today. And also, if you haven't already, please make sure to subscribe to our YouTube channel and comment what you thought about our today's meetup or what you think about our Zoom format. Also, please join us for our next talk on Wednesday, May 20th, where we'll be having a talk on democratization of data and AI. Thank you all and have a good night.
Thank you, guys. Stay safe.